Season, I am also a final year student of the University of Guyana. Presently, in fact, I'm no longer in Sir John Moses' class, who taught us topology, which was quite interesting in our fourth semester in our final year. It was very much interesting. We were able to apply concepts of mathematics in terms of application purposes. Logically, we were able to think abstractly and deal with the issues relating to topology. Well, before I go further into my presentation, I will be looking at the discrete topology. Excuse the handwriting. Okay, let me brainstorm you. What do you understand by the word? We're going to separate it discrete, and then we're going to look at topology. What do you understand? Anybody? What does the word discrete means?
Discrete is a word that contrasts with continuous. So discrete means that it's not continuous. It's not fully connected. It's points.
It's points. Okay. Anybody else? They're parts. Subsets. Good. So good. Well, all of that we can take and put it in a nutshell. Right? It's final. It's a point. Good. So in topology, we have the discrete. A discrete topology is said to be, let us say, let X. We have exhausted X in the morning. Let X be a countable set. The word countable means that we can, it's finite, right? Then tau, right, equal is a discrete quantity. This P of X represents the power set of X. Power set means that it's a subset of X. Right? Mathematically, we know that if we have a set, let us say set A is equal to 1, 2, 3. Mathematically, how many subsets will we have from that? 9 is incorrect. 8. Because what is the formula mathematically?
2 to the n power.
2 to the n power. And when we list those subsets, what do we recognize? What are the rules governing the subsets when we list them mathematically? And what else? The empty set and the set of itself, right? Right? Makes up the subset. Same thing in topology. We said that the power set of X represents the subset of X. Right? So let me take X is equal to A, B, C. Right? The power set of X will give us what? We'll have A, we'll have B, we'll have C, we'll have A and B, A and C, we'll have B, C, A, B, C, and we have one more, which is our empty set. So we have 8. Now, how will we know that it's a discrete topology? Right? How will we know? For the entire presentation for the morning or for the time I've been sitting here, we learned that for it to be a topology or topological space, we have to have certain axioms have to be satisfied, right? The first axiom says that X and phi must be an element of tau. The next one says that UI, the union, finite union, must also be an element of tau. And the final one says that the intersection of all i's or ui's must also be an element of tau. So now this is all the sets here. Should get a colored marker. I can name these sets, these subsets within this entire set here. Let me say I call this U1. This can be U2, right? U3, on and on, right? Till up to UN, up to where we stop. Now if I take the first condition, or the first axiom to prove if it's indeed a discrete topology.
That's okay. Don't worry.
Yeah.
Don't worry.
So the first one, we clearly know that X was equal to A, B, C. I erase it just. A, B, and C. We said X was that from the beginning, right? So we're proving the first axiom. Clearly, you can see that X and phi is an element of tau, because in tau we have what? X. Right? So we know the first condition or the first axiom is indeed satisfied. If we take the second axiom, let us say U2 union U3. U2 is A, union U3 is B. C, sorry. And if we take this, we have the union of A union B will give us what? AC. Right? Is this an element of tau? Yes. So it's also an element of tau.
Okay.
Right?
Okay, let us assume that all the conditions are satisfied.
Yes, sir.
What makes it to be discrete?
So once all the conditions are satisfied,
Yeah.
it is a discrete topology.
How do you say that? Because they are the conditions given are
they're subsets of the original set, which is, let's say, X, as what I said in the beginning.
So, according to you, any topology can be a discrete topology.
Any topology can be a discrete. No, sir. Not any topology can be a discrete topology.
Why?
Because you have different types of topology. In this case, it's a discrete because it's final. We can count